Welcome you all. Myself S.S.Mahamuni, Assistant Professor from the Department of the Pharmaceutical Chemistry, Satara College of Pharmacy, Satara, affiliated to Dr. Babasaheb Ambedkar Technology University, Lunere. Today we are going to see the practical of the subject Instrumental Method of Analysis from the final year B Pharm. The exam number is 7th, that is estimation of sulfate by the nephelometry. So we will start with the first, that is aim. So aim of the experiment is that to estimate the amount of sulfate present in a given sample by nephelometry. In that we want to estimate the amount of the sulfate ions present in a given sample by the nephelometry. Then we will move toward the next point, that is objective. So there are two objectives. First is to understand the principle of nephelometry. Then second is to understand the instrumentation of nephelometry. Then we will move toward the main first point, that is principle. So nephelometry is an example of instrumental method which is mainly used for the analysis of suspension. So we can analyze the suspension by using the nephelometry. So in a sample form, nephelometry means the measurement of opalescence or turbidity of a suspension. Means we measure the opalescence and turbidity of a suspension by nephelometry. And the sulfate ion is determined by the nephelometry and following the formation of barium sulfate. Means barium sulfate is formed in this suspension and that will give the information about amount of the sulfate ion present in that sample. So this turbidity is a white in color and consists of the extremely fine particles. Means turbidity is formed of barium sulfate and that ultimately gives the information about how much amount of the sulfate ion present in that sample. So to stabilize this turbidity or suspension, a glycerol and alcohol solution is added in this solution. So the main principle is that so light whatever the scattered is measured in this nephelometry and that scattering is occur due to the suspension is formed and that suspension is nothing but the turbidity or opalescence. So the light scattering is occur due to the turbidity and opalescence or the particle present in that suspension and that is measured and that intensity of that turbidity and opalescence give the information about the amount of that ions present in this sample. So sulfate ion also measured by this principle. Then we'll move toward the requirement. So first is the glass vase. So volumetric flask, pipettes, beakers, measuring cylinder, etc. we can use for this practical. The next requirement at chemicals. In that we use sodium chloride, hydrochloric acid, potassium sulfate, barium chloride. In that we want to use different types of the reagent. First is the sodium chloride HCl. So we want to prepare that sodium chloride and hydrochloric acid reagent. So we want to dissolve 60 gram of analytical grade quality of sodium chloride in a 200 ml of distilled water and we add 5 ml of pure concentrated HCl or hydrochloric acid and dilute to 250 ml. Means simply we want to take NaCl in required amount and dissolve in water and in that water we add the pure concentrated HCl. That's all. The next is barium chloride powder. So we want to reduce the size of barium chloride powder. So we use the analytical grade quality of barium chloride and that passes through the 20 mix sieve and are retained by the 39 mix sieve. So it will use the fine powder. Then next is the glycerol ethanol solution. So this is the preparation of glycerol ethanol solution. In that we mix 1 volume of the pure glycerol with the 2 volume of the absolute ethanol. In that we use the proportion 1:2. So 1 part of glycerol and 2 part of the ethanol. So next is that preparation of standard sulphate solution. So it is nothing but a standard stock solution of the sulphate. So in that we want to dissolve 1.814 gram of the analytical grade quality of the potassium sulphate in a distilled water first of all, which add 1 liter in a volumetric flask. So we want to take 1 liter volume of the volumetric flask and we add 1.814 gram potassium sulphate in that. So it will forms the stock solution. So this solution contain 1 mg per ml sample, so that it will form 1000 parts per million stock solution. So we can use further for the calibration curve and determination of unknown concentration of the given compound. So we'll see in next, that is first is procedure, that is A, for the construction of calibration curve. So by calibration method, statistical method, by using this calibration curve method, we can find out the unknown concentration of that sulfate ion. So we want to run 0.5, 1, 1.5, 2, 2.5 and 3 ml of standard potassium sulfate from a calibrated burette into the separate 100 ml volumetric flask. So we add first of all 0.5 potassium sulfate into 100 ml volumetric flask. As like that we make a different dilutions. Here is the process of the procedure for the dilution. For that purpose, we want to take first of all 1000 ppm solution, which is of a stock solution. From that we take 0.5 and we add into the 100 ml conical flask, and volume is make up to the 100 ml, and it will forms 5 microgram per ml solution. As like that we easily do the dilution for 1, 1.5, 2, 2.5 and 3 ml from your standard solution, and it will form 5 microgram, 10, 15, 20, 25 and 30 microgram per element solution, and that will used for the calibration curve preparation. So we will take all the observations of the turbidity for this 6th dilution, so that we want to move towards our earlier procedure, that is then we want to do the next step, that afterwards to each flask we add 10 ml of the sodium chloride hydrochloric acid reagent and 20 ml of glycerol ethanol solution and dilute to 100 ml with the turbidity free distilled water. So we add all this reagent, and then we add 0.3 gram, that is 300 mg of the sieved barium chloride powder to each flask, and we stopper and mix the content of each flask for 1 minute by intervening and making upright each flask once per second, so that we will get the proper diluted compounds for 0.5, 1, 1.5 and 2, 2.5 and lastly 3 ml. Afterward, allow each flask to stand for 2 to 3 minutes, then adjust the set control of instrument with a blank. So before going to start the experiment on that particular nephelometer, we want to adjust the zero control. Yes, so we want to use the blank solution without the sample. Afterwards, we with the standard solution of a highest concentration, we adjust the set 100 control to get a 100 display on the readout system. Means first of all we do the blank or we control the bank for 0, and after we take a highest concentration to make it a 100 on a display recorder, so that it will get calibrated our instrument, then we use for the further measurement of all these concentration we prepared earlier. So now measure the turbidity value of for each for other known concentration, enter the value in a tabular form, and from the data draw the calibration curve, that is concentration versus turbidity. So next part of the procedure is that for the analysis of a known sample, so transfer the known volume of the sample solution and make it up to mark, that is 100 ml turbidity free distilled water. From that, take a known volume of the treat as a given, measure the turbidity and calculate the concentration of the sulphate for the turbidity of the unknown from the calibration curve. So this is the procedure for the known sample. Then these are the dilutions. So these are the observation. It will come from the Nephelometer, that is turbidity. Concentration is here in the first column and second column is the turbidity. Afterwards, we put all these values in a graph, that is concentration versus turbidity, concentration on x-axis, turbidity on y-axis. We put all these values of that turbidity and it will form this such type of a graph. And afterwards we draw the line which is come from the origin of, that is from 0, and it will show the 3 points are properly gone from that line of origin. Afterward it will be useful to understand the unknown concentration if we extrapolate the graph for the value of 9.5 which is come from the unknown turbidity, and after extrapolation it will give 27 microgram per ml as the unknown concentration, as like this. So this is of the unknown concentration which is calculated or even find out or determined by the calibration curve method. And you also calculated from the theoretical, that is from stock solution we take 2.7 ml and volume is marked up to the 100 ml conical flask, it will give 27 microgram per ml solution, as like this. So I think all of you understand this particular nephelometric measurement of unknown concentration. So result may be the amount of the given sample by the nephelometry was turbidity is